start recording. Okay, so 2015, question 4 is a differential equation question like the one we just did. It says sketch a slope field. I'm not going to do that because I don't even have the slope field. But remember, all a slope field is, if you have a point, for instance, 1, 1, you plug that into your derivative, that's going to give you 2 times 1 minus 1, which is 1. And you draw a slope of 1 there. Boom. If you have the point 2, 1, which would be right there, if you plug that in, you're going to get 2 times 2 minus 1, which is 3. So you draw a slope of 3 there. And just go to each point and do that. I don't know what the slope field for this question looked like. It's usually only like between like 6 and 10 points. All right. So another thing they ask you, which they like to ask, and they didn't do it in this one, but they'll say, like, describe all points in the slope field that have a positive slope or something like that. Okay, so if you have to talk about all the points in this slope field that are going to have a positive slope, all you really need is the derivative to be positive. Okay, they could also ask you describe all points that have horizontal tangent lines. Well, then you need the derivative to be equal to 0, right? All points that make that happen are simply going to be when y equals 2x. So that's going to be on the line y equals 2x. Okay, so if you took any point on that line, y equals 2x, for instance, 2, 4. So 2, 4, right, would be way up here. If you found the slope there, you would get 0. Does that make sense? If you wanted the slopes to be positive, which again, they didn't ask, but they could, then you need the derivative to be positive. So we need any point that's above the line y equals 2x. Below, that's less than. Come on, Mr. Smith. We want y to be less than 2x, which makes sense because over here, see how the slopes are positive? But if I took a point above it, like 2, 5, you would see a negative slope there. All right, and if they asked you describe all points where the slope is negative, same thing, it would look like that, which would be y is greater than 2x. So you want all the points that are below the line 2x. Above the line 2x. What am I saying? Good God, yeah, I just said that. Yeah, above the line 2x. Okay, anyway. Sometimes they make it even easier too. Like if they give you a derivative is just like x times y and you want that to be positive, well, that's either when x is positive and y is positive, so quadrant 1, or when x is negative and y is negative, quadrant 3. Anyway, they don't ask us that. They just say, hey, find the second derivative. So let's actually do the question, right, Mr. Smith? Sure. So the derivative is 2 minus the derivative of y, which is dy dx, which is 2x minus y. Okay? And it says, determine the concavity of all solutions of the given differential equation in quadrant 2. Well, in quadrant 2, guess what we know? We know x is negative and y is positive. Okay? Since our second derivative is 2 minus 2x but plus y, right? If x is negative, that becomes 2 plus something, and if y is positive, that's also positive, so adding something. So the second derivative is a positive number. What are they? Right? Determine concavity of all solution curves. So all solution curves in quadrant 2 are concave up. Okay, that's all. That's all I want you to do there. Let y go f of x be the particular solution differential equation with the initial condition f of 2 is 3, so they gave me a point. Does it have a relative min or max at 2? Justify your answer. When you plug in 2, 3, this is a weird one, right? So you don't expect them to do this. You don't get 0 for the derivative, right? When you plug in 2, 3, you get 4 minus 3, which is 1. So neither. Neither. Remember, to have a max or min, the derivative has to be 0. Since dy dx at the point 2, 3 is 1, which is not 0. Okay. Now, if the derivative were 0, we'd have to check the concavity. However, the derivative was not 0. And then D says find constants for m and b where that's a solution to the differential equation. Now, that seems a little tough because we've got all these freaky variables floating around, but here's what this means. It means if you derive that, so dy dx, you're just going to get m, right? If you derive a line, this is just a line. If you derive it, you get m. But because that's a solution to the differential equation, that has to equal what they said the solution was, 2x minus y. That's the first key thing you got to recognize. The second thing is, we still got all these variables, but y has to be this thing right here, which is mx plus b. In parentheses, get out of here. So the only way m can equal 2x minus mx plus b, let's do this over here. That's the same thing as m is 2x minus mx minus b. So m, again, is just some number. I don't know what it is. But the way you solve this when you got all these variables, it's kind of like we did with partial fractions a little bit. All the x's on each side have to balance out. Okay, so here's what I mean by both sides. There's a left side and a right side. On the left side, there's an m. On the right side, there's a 2x minus mx minus b. Because there's 0 x's on this side, there must be 0 x's on this side. Now you see x's there, right? 2x minus mx, but they have to cancel. That means that 2x minus mx has to equal 0. Okay. Another thing to do is you can plug in any x value you want here, but if you drop, look, imagine plugging 0 in, you're going to get m has to equal negative b. So that is also going to be part of this. But when you do this, 2x minus mx has to equal 0. You get that m is better equal 2. So now we get this. 2 equals 2x minus b. But that means 2 equals negative b. So m is 2 and b is negative 2. So it's 2x minus 2x minus 2 is the answer to that. And you can check it as well, because if you derive it, oh, no, that's recycling again. Oh, well. I hear the truck out front right now. But if you derive that, you get 2, right? And that does happen to equal what it says the derivative should be, which should be 2x minus y, which is 2x minus 2, which tells us 2 equals 2. So it checks out. That's how you would check that.